indicator, which was based on energy and not on geometry. And the idea was basically to put 4 tetrahedral points around the water molecule and to evaluate the interactions it feels at each of these 4 points and order them from the strongest to the least interacting one. So we are going from B1S to B4S. And we define this last one as the index we are going to look. This is what we got for bulk water. And you see that basically we have a bimodal distribution where the first peak basically coincides with the linear hydrogen bond. And here we have another broader peak, which is related to molecules who have lost one of their interactions. And here we are, for example, considering the behavior of the 2 kinds of molecules. These are tetrahedral molecules, which have intact 4 hydrogen bonds. And these are the defective ones. This is for different temperatures. And this, you see here that this peak is basically at the same place for all temperatures. And here we are minimizing, while here we are taking the real dynamics. It does not move even with the minimization, while this one improves. And this tells us that, okay, the water molecule has 2, since we are looking at interactions, the water molecule has 2 interaction demands, 2 requirements. Either you form a linear hydrogen bond, or else you need some kind of compensation for the lacking side. And this is embodied in a molecular principle which is relates energy with structure. The second shell is the one which matters, since if you are going to form a good hydrogen bond, you need expansion of the second shell. This was already known for years. But it is interesting that if you are lacking a hydrogen bond, the second shell shrinks in order to provide some kind of energetic compensation. And this is what is happening here for these molecules. And this is not trivial. This is more than twice KT. So it's relevant. These molecules here are basically very akin to the low density ice, and these are very similar also to high density amorphous ice. Sorry. Here are the GDR, but we saw this on Tuesday, I think. Okay. I think we were here, but this is an anticipation of what I was going to talk. The idea is that going from one molecule with 2 liquids, we are thinking of one molecule with 2 interaction requirements. And if this happens in bulk water, well, does this translate into its behavior when water interacts with other kinds of molecules, with surfaces, for example? The idea is that do you have to satisfy these 2 requirements when water interacts with other things? Well, that's what we're going to see. The idea is that these 2 requirements translate themselves into 2 different hydrophilic limits, or 2 wetting behaviors. And that's what we are going to see from now on. The idea is to try to search for fingerprints of hydrophilicity. Since, you know, as we saw in the last talk, it is easy to have an idea of what is hydrophobic, what is hydrophilic, but is there any molecular descriptor that is telling us that you are being hydrophobic or hydrophilic? There's none. Well, maybe we can provide some kind of answer to this burden. Well, these are the applications of the index. Here, for example, we are looking at the behavior of water in contact with a graphene surface. Graphene, who are not in the field, has been, everybody thinks it's hydrophobic, but in the course of time, people have found that the contact angle measurements could not be performed in the, as it should be, since you need very clean surfaces that are not contaminated by the hydrocarbon from the air. And if you do that, such measurements very clean and without aging, you measure and don't at the first times, you have very hydrophilic behavior, very low contact angles, which grows, ages in time. And then you get a hydrophobic behavior. Well, but this hydrophilic behavior is some kind unexpected, since it's made of apolar, it's an apolar system. So this brings again that point. Apolar and hydrophobic are not synonyms. Okay. But when water is in front of one of this, is hydrating one of these surfaces, a graphene surface, it's going to lose one hydrogen bond, and it recovers interactions with the, it recovers some part of this loss when it interacts with the carbons of the surface. You know, carbons are very close to each other, so there's a high density of carbons in graphene. So one water molecule is going to interact with many carbon atoms. These are very, these interactions are very weak, but when you add up all of them, they are not so weak. But yet, the percentage you recover when you interact with the surface around from around 40%, the energetic loss of the energy of losing one hydrogen bond. So in some sense, it seems that it's quite strange that you would not expect a hydrophilic behavior for graphene. And this is one measure I showed with you before, that this the probability. This is the probability of cavity creation, to have to look at the probability of emptying a small observation sphere tangent to a surface. And here we are looking at graphene, and also two of the self-assembled monolayers I showed with you yesterday. This is ended in methyl, so this is hydrophilic, and this is ended in oxidryls, is hydrophobic, and this is in oxidryls is hydrophilic. And this is what you get when you look at the density fluctuations, or the probability of cavity creation. This is, and this is bulk water also. Bulk water, the hydrophilic sum, graphene is pretty close, and then the hydrophobic sum. So graphene is behaving in a quite hydrophilic manner. So when you look at the index, you have this kind of behavior. This is bulk water. This bimodal distribution. Here would be the high density, high local density molecules. And here are the well-ordered ones, the tetrahedral molecules. And when you look at this is the hydrophobic sum. Of course, it's at a very low value, close to KT. And when you look at the index for the hydrophilic sum, it behaves pretty much similar as the bulk water in a very hydrophilic manner. And when you look at graphene, you have this kind of behavior, and with a peak here, which, okay, it's well to the right, but it's clearly above this threshold. This threshold is around 6 kilocalories per mole. It corresponds to these kinds of molecules here. Sorry. Here. And graphene is 2 kilocalories per mole to the left. So this is a first hint that this index is somehow working as a measure of hydrophobicity, hydrophilicity. The point would be that you do not need to fully recover the hydrogen bond, to replace the hydrogen bond. If you mimic at least the behavior of the high-density molecules, you provide an environment similar to the one the water molecules find when they are in bulk in the disorder or defective configuration, it is enough to behave in a hydrophilic manner. Yes, yes, it's much more like high-density water at the surface. And we're going to see other examples. Well, this is another example. These are very old simulation by Umer et al., who found that, well, when you have a very narrow carbon nanotube below 1 nanometer wide, water enters, fills the carbon nanotube. That was rather unexpected, since if you have a system that is really hydrophobic, in this, and the pore of this dimension, water does not enter, since it's not going to sacrifice 2 hydrogen bonds to enter here, since, you know, you can see here each water molecule enters in a train that is attached by hydrogen bonds with 2 other water molecules, but it has lost 2 of them. The loss, again, is very relevant, around 60%, and what you recover is, with the interaction with the surface, is much more or less than that. So here what we did was, well, as if you here what you see, this is the number of water molecules inside the carbon nanotube, and you see that it's always populated. But if you weaken artificially the interactions, for example, the depth of the, if you cut to 1/2 the depth of the carbon-oxygen interaction of the Lennard-Jones potential, you get this behavior. It's almost all the time empty, sometimes enter, but it goes away very quickly. Dissolves. So what we did was, well, just change smoothly in a gradual manner the value of epsilon, the attractions with the wall. This is what's happening, what's shown here, and this is the number of molecules. Of course, when the interaction is larger, this is a normal value, it's always filled. Then you have a transient filling behavior at intermediate, it would be an intermediate case here, and then you get empty at certain point. This is what we get when we calculate the B4S parameter. And you see that basically when this, here you will have a regime marked by a very strong hydrophobic behavior. This value here is very close to what we get for the hydrophobic self-assembly monolayer, and it's very close to KT. But if you look at this line here, this is basically the field regime. The field regime basically coincides with -6 kilocalories per mole, which corresponds to the value of the compensation received by the high-density molecules, the effective molecules in bulk water. So again, you need such kind of compensation. But we are going to see that you need 2 of them, since you are losing 2 hydrogen bonds here. What you see for B4 could also be seen for B3. So basically, they are going to be quite similar, and I'm going to show them. Here is, for example, the number of molecules inside the carbon nanotube as a function of, here is the Lennard-Jones interaction, the depth of the Lennard-Jones interaction, and here is as a function of B4. Again, you are empty, 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 and then here at around 6 kilocalories per mole, you get filled. So this value is, in fact, acting as a threshold limit for wetting. This is another exercise we did, that is, instead of smoothing gradually all interactions, well, take some carbons and change them to half their normal value. These are all normal. Here, the red are the one we weakened. We weakened to 1/2 of their interaction. And here we are changing a bit less than half of the carbon atoms. And here we're changing many of them, 64%. And what you see, we plot here the values of B4S and B3S you get. In this case, both of them are below -6. When you go to, and here is 100% full. This is the normal carbon nanotube. In this case, you get 93% of the time the carbon nanotube is full. It's almost all time full. And again, well, both of them are here. B4 is beginning to go below this threshold, but B3S is still to the left. And when you go to this case, you have very poor statistics here, since 81% of the time it's empty. It's most of the time empty. And what you see is that both of them have crossed the threshold. So the question is, what do you need to wet? How much interactions does water need in order to wet? Well, you can only sacrifice one interaction at the level of the defective molecule. If you sacrifice two of them, you're not going to be good at wetting. Here, you are sacrificing two, but the two of them still are above the threshold. Here, the two of them have crossed to the other side. Okay, very quickly, this is another system. These are self-assembled monolayers where we carved a hole and we put an observation volume there. And what we did is, well, we calculated the B4S index for holes of different sizes. When you have a small hole, it's going to be quite hydrophobic, we expect. And the system is always hydrophobic. These are, they are methyl-ended SAMs. They are hydrophobic when they are plain, without hole. But when you get the hole, we expect to be more hydrophobic, of course. And this is what you get here. This is the probability of cavity creation. To have this sphere here empty. And you see that, don't pay attention to this nomenclature, but basically this is the diameter of the pore. And you see that you at first, it's almost always empty. When the pore is very low, very small, it's always empty. And it begins to go to a value that it's, well, the limiting value for this self-assembled monolayer. And this is what we get for, sorry, I had to, well. And this is how we correlate the probability of cavity creation. This logarithm is related to the work for water remotion. And you see that it's a nice correlation with the B4S index. So this tells you that the index is performing as a good predictor of the level of interaction of the hydrophilicity of the surface. This is a very interesting effect. The effect of the dense carbon network on graphene. When you look at the water molecule, which is over a graphene surface, you find that basically it slides over the surface. And that's a behavior that is more typical of hydrophobic systems. But when you calculate the probability of cavity creation, you get a hydrophilic value. So here you are having some kind of combined behavior. And what we did was, of course, here it is. You look, it behaves like hydrophilic, but molecules move here very quickly. If you have here a very hydrophilic surface, the water molecules attach to the surface by, for example, hydrogen bond, and they stay there until they are detached, but they don't wander over the surface like here. Here, basically, we have, I didn't put a movie, but it's like this sliding over the surface. And this is, if you look at the mean square displacement in the parallel direction, parallel to the graphene layer, and here we also show the normal direction, you see in the parallel direction, there's a slippery for graphene and the hydrophobic monolayer. and there's no slippery for the hydrophilic monolayer. So this is also shown here, this behavior. But when you look at the normal direction, which would give you an idea of how difficult it is to extract a water molecule from the surface, would be related to the hydrophobicity or hydrophilicity of the surface. The behavior is opposite. Since, again, you have the two limits, this is the hydrophobic, this is the hydrophilic, and graphene is very close. Even below, it's strange, but it's very, very close to the hydrophilic. So here, the molecules move. They are not attached to a site, but it is very difficult to create a cavity, since when the water molecule moves, another one is replacing it. And why is this molecule doing this? Well, because it is not attached to just one site, but it is interacting with many carbons at the same time. With many, it's a sum of many, around 10, 15 interactions. And you are not cutting a bond in order to move. You are replacing interactions. So it's easy to move at the surface. But this is related to hydrophobicity, since, for example, if this were another system, it could be interesting, but it would be, for example, a protein. But it's also interesting in the cases of when you want to interact, for example, a contaminant molecule or so. It's not as easy to remove to replace water molecules, since when you are going to bind to the surface, you need to, there is a cost in removing water molecules. Here, molecules move, but it's very difficult to remove them, while in the other case, when you are over a hydrophobic SAM, it's easy, since the molecules easily go to the bulk. And this behavior would be related to the nice properties of graphene and graphene-based materials, in the sense, for example, how it's easy to flow in a nanotube, or also how good they are for absorption, since if this is this happens for water, it also happens for other molecules attached to the surface. For example, I'm going to study, but we can. Yes? What?
Do you think using a reactive potential, the hydrophilic surface maybe presents more difference in the emissivity?
It's probably, yeah. It's probably. But the point, not in the slippery, since this slippery behavior, after publishing this paper, I found a paper from another group where they show it that, for example, it was, I can't remember the system, but it was an oxide, so it was quite hydrophilic. And they said, oh, we can get hydrophobic behavior in a hydrophilic system, since they artificially shortened the parameters so that the atoms were closer. And when you get the atoms closer, again, this effect is, they didn't explain this effect, but they also found that water slipped over the surface, even when it is quite hydrophilic, since they had very strong interactions with the surface. It's a matter of the density of the surface, not on the interactions. Okay. Well, very quick, since I'd like to have time for the hands-on, so I have to be quick. These are also some preliminary studies. This is a study of protein hydration water. We were focusing on whether a long time ago, when I was more on biophysics, we studied hydration of proteins, and we were aware that hydration can tell you something on the surface of the protein, maybe related to certain, you know, basically the protein surface is mainly hydrophilic, and the hydrophobic groups tend to be in the interior, since these molecules are soluble and they self-assemble in order to be soluble. But when you have a binding site, for example, you expect that this site is going to be more hydrophobic, since if you have a ligand that's going to interact, it's good to have dehydration, since interactions in a dehydrated environment, interactions are strengthened. In some sense, the local dielectric goes down. In fact, it's easier to drag an enzyme which has a pocket where the site is a small pocket, which geometry has made the job. It has dehydrated the system. It's really very difficult to design drugs that disrupt protein-protein interactions, since protein-protein interactions tend to be more flat. And you have this problem. You need some dehydration. There are some theories where they speak of a kind of O-ring, in the sense that you have reactive site that is somehow protected by other residues, that much of them tend to be hydrophobic. And well, what we did is, well, look at some protein, the hydration layers of certain protein. This is what we get for a bromodomain protein. Here we are showing the before-S distribution for hydration for different layers. This is for hydration layer. We were picking up hydration layer very similarly to what Paola said, since you find a change that is very quick. At around 3, 4, 5 angstroms, you have one kind of behavior, and then goes quickly to bulk. And this is what is seen here. But that was not what we were more interested. This is an interesting point, but we were interested in trying to see, well, is this metric going to tell us anything on the binding site? Can you somehow predict where the binding site is? Of course, we know where it is, but we performed this analysis, and what we did, this is the same here for different 3 proteins, but when we are looking just at the hydration layer, and the behavior is very, very similar. And for this protein, for the bromodomains, this is what we get when we look at the binding site, the statistics is lower since the binding site is smaller. And when we look at the rest of the surface is going to behave similarly to this hydration layer, but at the binding site, you see that it has moved to the left. So you have a higher concentration of high density like molecules at the binding site compared to the surface. And this is what we also get for another protein. The situation is very similar. This is what you get as here or here. And when you look at the binding site, it has moved to the right. So the binding site is enriched in high density like molecules whose before S is below it's around -6 kilocalories per mole. This could be the protein surface, and you are somehow in a binding site which tends to be more pocket-like, but it's not necessarily the case. Quickly, this is the binding site for one of these bromodomain proteins. And here is co-crystallized with a ligand. And what we are looking here is in red are the regions where you have a high, when you accumulate high density like water molecules, and in blue, places where low density water molecules accumulate. And basically you see here that where this molecule presents a hydrophilic residue, you find regions that are blue, that are rich in low density water. And there are other regions, for example, here you have this ring that is hydrophobic and it's red. When you look at we do analysis without the ligand, of course, and you find many red molecules, which are molecules with a low index value. They are high density like. It's interesting, for example, that here we find a region where very red region, and this ligand is not covering this region. It could be perhaps interesting to try to put, to re-engineer this ligand in order to include here a residue that is hydrophobic. So maybe this kind of analysis could be of interest in studies of drug design or drug re-engineer. But these are very preliminary. We also plan to study what happens in proteins with Paola when you go to the glassy regime to show, well, what happens to the surface, how is the concentration of both kinds of molecules, and even perhaps the protein transition, or that would be very interesting. Okay. Well, this is another very recent result, very beautiful simulations by the group of Rafael, Mateus, and Patrick. I'm showing just, they did all the work, but they asked us, well, you have this metric, can you tell us something on, is it working here? Can you? The point is that when they had carbon nanotubes and they looked for the absorption of a diclofenac molecule, they found that the absorption was positive, so it was successful, and they had difference when I'm going to get into the details, but one of the messages was that when you have a double-walled carbon nanotube, the absorption was better than, they had a barrier for binding that was larger than in the case of the one-walled carbon nanotube, and they expected this to be related to how easy it was to remove water from such site in order to bind. And it's very interesting that when they saw us the movies, the diclofenac molecule is large, also is dancing over the carbon nanotube. I say, oh, God, it's a Brazilian diclofenac. But this is related to the same point that we talked before, is that you have many interactions, and you do not need, in order to move, to break interaction completely and reform at any place. You are just changing some of them, and you move. Okay, this is very preliminary. Our results were a bit modest, but they seem to show certain differences. We calculated, for example, the probability of cavity creation. They are a bit different, and also the mean value of B4S in the two cases, the single and the double layer carbon nanotube. And it seems that in the case of the double-walled system, water molecules are more attached to the surface, so the barrier for their removal would be a bit larger. They found that the diclofenac molecule bounced very many times before being able to bind. And when you had it binded, it began to dance. So, okay, but let us go to the last part. Okay, I showed this picture before. This is the usual measure in solid surfaces, the contact angle measurements. This is a quote from a commentary in Science from Granick and Bai, who said, okay, everybody seems to know what is hydrophobicity, but it depends on, everybody thinks of kind of different definitions. And when you go to a measurement that tells you how to to quantify this effect, we find nothing. Okay, you say when you have here a contact angle that is 90 degrees, you are below this value, you are in a hydrophilic situation, and when you're above that value, you're in a hydrophobic situation. But do you see anything? Is there any molecular descriptor that is changing when you cross this limit? None. Well, we thought that this was a good test for our ideas. Our idea is that, remember, water molecule has two expectations. You fulfill a hydrogen bond completely, or else you should pay certain compensation to have a lacking site pointing to you. So this we are expecting that this compensation, this about around 6 kilocalories per mole, that is pretty temperature independent, is going to perform as a wetting threshold. Okay, this is what the group of Garde, who worked in who introduced the probability of cavity creation calculations I showed you before, made molecular dynamic simulations of droplets above different kind of self-assembled monolayers that are, for example, these are very hydrophobic. For example, there's a methyl here. These are very hydrophilic. Hydroxyl here, and they have a battery of different situations. And okay, you find the behavior is nice, it's linear here, but you have some discrepancies. See, for example, everything above 0 would be classified as hydrophobic. 0 would be higher than 90 degrees. And sorry, this is experimental. But then when you go here, this is the hydrophilic region. So this is close to, this is 90 degrees. This is close to 0 degrees, because this is cosine of the angle, the contact angle. The hydrophilics are here. And you see these two ones are going to be taken as, in the molecular dynamics simulation, as a bit hydrophobic, while they are hydrophilic in experiments. And it tells you nothing on if anything changes here. Nothing changes here, it's just that you have different values. Okay, and it's very nice to have these points here, since, for example, this one was very interesting for us, the methoxy functionalized sum, since, you know, it's sitting on the verge of, on the verge of hydrophilicity. Here would be the change from hydrophobic to hydrophilic. So it's a very interesting point to study. This is what we get for some of the self-assembled monolayers, just a few. Here is, again, we are comparing with bulk water. The dotted line here, this is bulk water. Yeah, bulk water for two cases, for the T molecules, the D molecules, and full bulk water. We are separating the two kinds, the high and low density ones. And here is, again, the hydrophobic monolayer, that's around KT. It's very, very hydrophobic. Here is the hydrophilic case, the oxidryl. It's very similar to bulk water. And this is what we get for the methoxy one. It's similar to the high density water molecules. Here we're comparing both of them. This is for the D molecules, the high density ones, and this is for the methoxy functionalized surface. In fact, the mean value for this is a bit to the right, as we expect. So this is a strong indication that the index is performing well in separating between the two kinds of behaviors. Here, what I'm showing you, in this case, they are number density fluctuation of water molecules, normalized by the mean value. And you see this is, this was for single monolayers. Then what we did, well, this is in the barrage, this one is on the barrage of hydrophilicity, hydrophobicity. Well, what happens if you have two of these monolayers and begin to bring them together? Of course, they are going to collapse, but is there some point when your geometry is going to spoil the interactions? And if you are very close to the limit, if your interactions are going to spoil in geometry, they can cross this limit. And then you're going to get hydrophobic, and you are going to get dissolved. And this is basically what we found, since this is the behavior for a hydrophilic case. This is the sum with hydroxides. It's always very low fluctuations. That is, water molecules fluctuate very little. It's very difficult to extract water molecules from the surface. This is what the case for the hydrophobic sum. Of course, if distance is large, you are like bulk in between the two layers. But when you approach the nanometric regime, we are going to have a few confined layers, and then the water molecules are expected to fill this hydrophobic confinement, and you are going to go out. At certain point below the angstrom, of course, you are going to be like in the carbon nanotube. Again, if your carbon nanotube were shrinker, if the radius shrink, it would be also dissolved. And what you see is that here fluctuations begin to grow quickly. So this behavior is quite hydrophobic. It's easy to remove. This water is easy to remove. But when you look at this case, the methoxy sum, you see that remains in a hydrophilic regime, remains until at certain point, around 8 angstrom separation of the two layers, it begins to increase quickly, as here. You begin to get a hydrophobic-like behavior. It's hydrophilic with a transition hydrophobic. When do you find this behavior? Well, here we show the number of layers. It's when you change from at around 8 angstroms, you have 2 layers, but when you go to 7 angstroms, you have only 1. So when confinement is very strong, geometries of interaction are spoiled. These interactions were, okay, we were hydrophilic, but just hydrophilic. If you spoil the interactions, they become hydrophobic. And when you calculate the fraction of molecules which are which are of D type, of the high density type, you find that here the fraction of molecules is around this value, and at 8, again, when this happens, they begin to increase quickly, and here very quickly cross the half the value. So they begin to dominate this interplate region. Of course, these molecules are going to be easy to remove. You have a transition, again, at this point, marked by -6 kilocalories per mole, you have a transition between a hydrophobic and hydrophilic behavior. This is what happens. In fact, you have the two populations again here, and you're transferring molecules from the low density side to the high density one as you get closer. Well, at H, you have 2 layers. So sort of the molecules can have more freedom to arrange themselves in order to still form good interactions with the surface. When you have only 1 layer, okay, you're here. So you have 1 layer here, 1 layer, you have to be good to the 2 of them at the same time, simultaneously. It's very difficult to do so. So this is speaking you that the interactions are getting worse. And if you spoil something that is very just hydrophilic, it gets hydrophobic quickly. And it's expected to happen there. You know, if you go higher separations, you have bulk behavior. But some, when you have 2 layers, perhaps there's some small change, but it seems to arrange to, it's fine for the water to adjust. And well, of course, the idea is what is telling us the index. Here we are correlating the experimental contact angle measurements with what we get with our index. You know, here we have basically a very nice linear behavior that would extrapolate here. And all these points here are for the very hydrophilic cases. This one, we don't have experimental values, but we calculated it anyway. All these are experimental, even this and this. And this would be a bulk case we also include in the plot. And you see that this is a saturation limit. This is a very strong hydrophilic limit. These guys are replacing a hydrogen bond, so they are behaving like bulk water. So, you know, 2 interaction demands: hydrogen bond or compensation. Or you shrink in bulk water, you shrink the second shell. Here, you have to compensate somehow. You have to mimic the energetic environment. You have to provide interactions of the same magnitude. And you see this linear behavior here, and all of them are classified according to the experiment. You know, all of these are hydrophilic, and for us, they lie here to the left. Yeah? And these are hydrophobic. They are on the other side. This is sitting almost in the limit. Well, we expect the limit to be somehow here. When they are crossing, they're not far. So you have one saturation limit, and you will have one transition here from hydrophobic to hydrophilic. So we have a measure that enables us to quantify hydrophilicity or hydrophobicity. And this tells you that you can indicate what's going to happen if you make calculations of the structure of water. This is also the correlation with the probability of cavity creations, P of n equals 0, which you remember that this quantity is proportional to the work of water removal, and these are the values of B4S as compared with this calculation from the group of Garde, which I showed you before. The calculations, not the contact angle, but the calculation they did over these kinds of the probability of cavity creation on these surfaces. And the accord is excellent here. And again, you get here kind of saturation limit. These are the kind of calculations. You look at the number, the n average, and you calculate when this is the probability is here 0. You are calculating the probabilities of have an empty void in the observation volume. And this also works good. So water is good at establishing interactions. You do not have to necessarily fulfill completely the hydrogen bond. Of course, that's the optimal expectation. But it also offers you an alternative. Okay, you cannot replace a hydrogen bond. But if you provide me an environment that is close to a defect, when this defect is in bulk, you're going to be hydrophilic. If not, if you're not able, okay, then you are hydrophobic. And as far as we, in the case we have proven, and this was a very nice test system, since you saw that we had many different hydrophobic, a wide spectrum, not many cases, but a wide spectrum of hydrophobicity and hydrophilicities, and one of them what was sitting just at the transition point we expected, and we saw the change were expected. So one simple molecule, two interaction demands, or two ways of lab to satisfy. So these two demands in bulk translate into two limiting wetting behaviors: saturation limit, or transition, or hydrophilic threshold, or transition for hydrophobic to hydrophilic. So at contact angle of 90 degrees, B4S is around -6 kilocalories per mole. It's like a bulk D molecule. So we are seeing some fingerprint, or molecular fingerprint of hydrophilicity. As Marcia asked the other day, there's something that, you look at here and you say this is hydrophobic, hydrophilic, but quantitatively. I show with you a lot of hydrophobicity scales that were most of them with relative values, since you don't have absolute scales. And even contact angle if it is quantitative, as the commentary I told you said, we don't see anything changing when you are at 90 degrees. Yes, something is happening here. So this not only would enable to find the signature of hydrophilicity, but also would be relevant to establish absolute or not relative scales of hydrophobicity. So we can skip this were very general. This would be the situation. So you are this guy, this water molecule is very happy. This one is kind of happy. This is low density, high density. It's okay, I have only 3 neighbors, but I'm fine here. You are at the surface. This is a hydrophilic surface. Okay, it's like bulk. Here, hydrophobic. No, I don't like this. And graphene, or other systems which cannot provide a hydrogen bond, still are able to give you a compensation close to this guy, and it's fine anyway. So this is the people of the group who work in this. I would like to thank, and most of all to the one who has most of the credit here, sitting here, Nicolas, who made almost everything. He's incredibly young and brilliant, and so thank you, Nicolas. And just to finish, I told you that I showed you a first slide in my first talk that was, a typical mandate in physics is to extract simplicity from complexity. We had a very similar question here. You have a very simple system. It's very simple from the structure. Water is one oxygen, 2 hydrogens. It's extremely simple, but it has a quite complex and beautiful behavior. How did nature cope with this? How was nature able to introduce complexity into such a simple system? Well, the idea was, as many guessed, go with interactions, introduce complexity with interactions. And here is somehow what we try to do. It's not just the hydrogen bonds are relevant, but also the hydrogen bond defects are relevant, since when you are going to have a lacking hydrogen bond, you have to provide some compensation. So interactions are relevant. Interaction of water with water and water to any other system. Interactions in real life are. So I began with this, the Canticle of the Creators of St. Francis, that said that praised be you, my Lord, for sister water, who is very useful and humble and precious and pure. And I remarked here, sister water and humble. So in some sense, this was in Raúl's Grigera book. He was a very wise man, so the hints were in some sense in St. Francis' prayer, since, you know, sister water and humble, interactions, humility, simplicity. You know, water, sor aqua, sorella aqua, sister water, is very simple, and what is relevant is to be simple, but to have complexity in the interactions. It is possible to have a very complex, a beautiful behavior, even being such simple as one oxygen, two hydrogens. Of course, but humility and interactions are not only a message for us who were trying to figure out the behavior of water and hydrophobicity and so on, and also it's a very interesting message for life beyond physics. And this is, you know, Argentinians are mostly known abroad by Maradona and Messi, who I love a lot, of course, but I think we should be better known by the Pope Francis, who is nowadays, in such a complicated world, is a necessary voice today. And he wrote his encyclics. One is called Laudato Si, and the other one is Fratelli Tutti, fraternity, sister water. It's not, well, my, and, okay, St. Francis mastered simplicity. He was very humble. And he also lived in a very deep level of interaction. He also mastered fraternity. Francis was a brother to everyone, to every man, to every woman, and also sister water, sister moon, brother sun, earth, birds, trees, even brother wolf. There's a very beautiful story of St. Francis with the wolf. And I would like to end with a phrase that was brought to us by Jorge Luis Borges in Pascal's Sphere, that said that God is a sphere whose center is everywhere and whose circumference is nowhere. Indeed, Francis deeply felt that center in every living system, in every being or entity around him. So this message is, well, water is telling something. Sister water is telling something also beyond physics. Okay, so thank you very much. Maybe I'm out of time, surely, no? But I would like to thank the organizers, since I'm very, very happy to be here. Paola and Marcia, I know them for many years, and they're extremely beautiful persons, so I was very happy to come here to meet with them, and also to meet other people. Rafael, who went to visit me, Bahia Blanca, he's a great person, and all of you. I'm very happy here. Really, Marcia did a great job. She had very beautiful atmosphere here, so I'm very happy. I did not used to collaborate with Brazilians in the past. It's a shame, and really I'm very happy to be here. And believe me that it's not just, okay, it's not, I'm not being polite. We have been, I think Nicolas also can tell you, I've been very, very happy here, and you genuinely made us feel like home here. So thank you.